How many Earths are there? This question, whether our planet is unique or just one among countless parallel versions, has inspired endless debate in both science and fiction. For decades, storytellers have explored the idea of alternate Earths and parallel universes, shaping a vast body of literature, film, television, and gaming that brings these possibilities to life. But beyond the realm of imagination, do parallel universes have any grounding in modern physics? Is it truly possible that our universe is one of many? Or is this concept fundamentally beyond the reach of scientific inquiry? Communicating the complexities of parallel worlds, or the broader concept of a multiverse, is no small task. Fortunately, physicists like Brian Greene have taken on this challenge, providing insights that are both accessible and deeply informed. Greene, along with other researchers, suggests that while the notion of multiple universes may appear strange, it actually aligns with a long-standing pattern in the history of science, one in which our perspective on our place in the cosmos has repeatedly been humbled. Over the past few centuries, humanity has experienced a series of cosmic demotions. We once believed Earth was the center of everything, only to discover that it orbits the sun. Then we learned that our sun is just one ordinary star among billions in the Milky Way. Next, we realized our galaxy is just one of billions more scattered throughout the cosmos. Following this pattern, it may not be so surprising if our entire universe is but one of many universes in a grand cosmic tapestry, a multiverse. For a long time, physicists regarded the observable universe as a single, self-contained entity, but a growing number of researchers now argue that there is a genuine possibility that parallel universes exist. Brian Greene has developed classification schemes to help us understand the various theoretical types of multiverses, each arising from different principles and models in fundamental physics. These classifications often rely on mathematics derived from quantum mechanics and string theory, suggesting that multiple quantum states or branches could exist simultaneously, each forming its own coherent reality. One route to the multiverse idea comes from the theory of eternal inflation. Inflation is the process thought to have happened in the earliest moments of the Big Bang, causing space to expand at an exponential rate. In the eternal inflation scenario, this rapid expansion never ends on the largest scales. While some regions of space slow down and form stable universes like ours, vast expanses continue to inflate, producing innumerable bubble universes. Each bubble could have its own unique laws of physics, arrangements of matter, and even fundamental constants. In this picture, what we call our universe might be just one bubble among an infinite cosmic foam. Another perspective uses a simple analogy. Consider a deck of cards. There are only finitely many ways to arrange the cards, but if you shuffle them an infinite number of times, eventually the same order must appear again. By analogy, if space is infinite, with particles arranging themselves in finitely many ways, every configuration must recur somewhere. That implies that at unimaginable distances, there should be regions of space where configurations of atoms are identical, or almost identical, to what we see here. This reasoning leads to the conclusion that somewhere out there, duplicates of you, Earth, and our entire cosmic history might exist. This reasoning also provides a potential explanation for a long-standing mystery. Why do the fundamental constants of our universe seem so finely tuned to allow life to evolve? If the multiverse is real, then most regions of it may be utterly unsuitable for life. We just happen to live in a rare bubble where the constants are right. This concept, known as the anthropic principle, posits that intelligent observers can only appear in universes hospitable to their existence, making our universe's life-friendly conditions less surprising if we consider a vast cosmic ensemble. Parallel universes also appear in the many worlds interpretation of quantum mechanics, proposed by Hugh Everett in 1957. In this view, every time a quantum event could produce multiple outcomes, all outcomes actually occur but in separate, non-communicating branches of reality. Each branch evolves into its own fully realized universe. According to the many worlds viewpoint, the universe is constantly splitting into countless versions. While most physicists historically favored the Copenhagen interpretation, which posits that observation causes a quantum system to collapse into a definite state, Some modern researchers, such as Sean Carroll of Caltech, argue that many worlds is more faithful to the underlying mathematics of quantum mechanics. How many universes would that produce? Potentially infinitely many. Even if finite, the number would be astronomically large, as universes spawn from the quantum possibilities inherent in every event, right down to radioactive decays in your body. Carroll likens it not to discrete, splitting events, but to a continuous whooshing of reality, subdividing into ever more branches. The complexity is staggering, and while it may seem extravagant to posit so many universes just to explain quantum behavior, proponents claim this proliferation of worlds was always implicit in the quantum formalism once we accepted that particles can exist in superpositions of states. Not everyone is convinced. Critics of the multiverse concept argue that it is not truly a scientific theory because it lacks testability. Some worry that embracing unobservable realms might erode public confidence in science or blur the line between physics and philosophy. They assert that without empirical evidence or a way to distinguish one cosmological model from another, the multiverse remains a speculative notion rather than a robust scientific hypothesis. Defenders counter that the multiverse is not invented out of thin air. Rather, they maintain that it emerges naturally from established theoretical frameworks. If inflation is correct, if string theory is on the right track, or if quantum mechanics inherently leads to branching worlds, then the multiverse is not an optional add-on. It is a logical consequence of these accepted ideas. We might never directly observe another universe, but that does not mean the concept is beyond scientific reasoning. Just as we accept aspects of quantum theory without directly seeing superposition with the naked eye, we might accept the multiverse if it offers coherent explanations for otherwise baffling puzzles. Still, the ultimate question remains: can we ever prove or disprove the existence of parallel universes? Without the ability to step into a black hole leading to another cosmos, or to detect signals from a neighboring bubble universe, we face deep conceptual and technological challenges. Perhaps future breakthroughs in gravitational wave detection, cosmic microwave background measurements, or subtle patterns in the distribution of matter might point indirectly to other realms. Or maybe physicists will develop ingenious theoretical tests that let us infer the multiverse's existence from its indirect effects. For now, the multiverse remains both tantalizing and elusive, a grand cosmic hypothesis that pushes the boundaries of imagination and forces us to reconsider fundamental assumptions. Whether we ultimately find evidence that we inhabit one universe among countless others, or conclude that the multiverse is a beautiful but untestable idea, the journey of exploring these possibilities continues to enrich our understanding of reality. Thanks for watching. If you enjoyed this deep dive into the theories and controversies surrounding parallel universes, consider subscribing and ringing the notification bell. By staying informed, you won't miss any future explorations of the cosmos and the fundamental nature of existence.